Next, let us try to understand what exactly we mean by ideal voltage source and of course practical voltage source. See, in the previous example which I took, we designed a source of 4 volt, but at the output how much we got? We got 3.40 volt. There is a drop of 0.60 volts because of the internal impedance of the source. So is that an ideal source? No, because if you produce 4 volt, the output should get 4 volt. There should not be any voltage drop. Such type of source are called as ideal voltage source. Now again we will go back to that example, that 0.60 volt drop was because of the internal impedance of the source. That means an ideal voltage source will be a source with Ri equals to 0. That means there should not be any internal resistance or internal impedance of the source. So when I design a particular source, ideal voltage source, this will be the diagram. There won't be any internal resistance. This is the input voltage and this will be the load resistance across which the output voltage will be taken. Okay, and let's say I will be the current which will be flowing. So I is equal to V upon R. Say V is equal to 4 volt, I is equal to 1 ohms. So it will be 4 upon 1, that means 4 ampere, and the output voltage across RL, of course in this circuit the only resistance is RL, so it will be V upon RL, V up 4 upon 1, that is 4 ampere. And what will be the output voltage? The output voltage will be the current flowing in the circuit multiplied by load resistance. So current is how much? 4 multiplied by resistance is 1 ohm, that means it will be 4 volt. So you have produced 4 volt, you have transferred the entire 4 volt to the output voltage. That will be an ideal voltage source. So in general we define that an ideal voltage source is the source where the internal impedance is 0. Now if we have understood the concept of impedance, this impedance is because of the component used to design the source, right? मतलब सोर्स बनाने के लिए जो कंपोनेंट हमने यूज किया है उनका जो अपोजिशन है वही तो इंटरनल इंपीडेंस है। तो बिना कंपोनेंट के सोर्स बना सकते क्या? नहीं। अगर आपने एक सोर्स बनाया है और एक कंपोनेंट यूज करके बनाया है तो वो कंपोनेंट का जो रेजिस्टेंस है वो तो इंपीडेंस रहेगा ही। मतलब एवरी source will have its impedance, right? And the second important thing is, suppose we consider a short circuit case. Short circuit means in electronics terms, between any 2 point, if the resistance becomes 0, say RL अगर 0 हो गया तो, right? तो यही फॉर्मूला में आप चेक करो, I equal to V upon RL. अगर RL गलती से 0 हो गया, anything divided by 0 is infinite. That means infinite current will flow in the circuit. That is not permissible. So in general we say ideal voltage source does not exist. क्यों? क्योंकि या एक तो आप अगर RL शॉर्ट हो गया तो करंट इनफाइनाइट हो जाएगा, जो होना नहीं चाहिए। दूसरा, कोई भी सोर्स इंपीडेंस जनरेट करेगा ही, क्योंकि वो इंपीडेंस उसके कंपोनेंट जो बनाया है, वो सोर्स यूज करके जो कंपोनेंट यूज करके जो सोर्स बनाया है उसके वजह से वो इंपीडेंस है, तो सबका इंपीडेंस रहेगा ही। मतलब आइडियल वोल्टेज सोर्स डज नॉट एग्जिस्ट। तो क्या रहेगा? ऑफ कोर्स देयर विल बी अ प्रैक्टिकल वोल्टेज सोर्स which has internal impedance as well as the voltage. So whenever you design a voltage source, it will surely have an internal resistance. तो प्रैक्टिकल वोल्टेज सोर्स को डिफाइन करते समय व्हाट वी डू इज, हम लोग बोलते हैं कि अगर आपका लोड रेजिस्टेंस इंटरनल इंपीडेंस से बहुत ज्यादा बड़ा है तो वी कैन प्रोड्यूस दिस कंडीशन, जहां पर हम लोग जो इनपुट में दे रहे हैं वही हमको आउटपुट में मिलेगा, राइट? सो दैट इज व्हाट इज कॉल्ड एज प्रैक्टिकल वोल्टेज सोर्स। सो प्रैक्टिकल वोल्टेज सोर्स मतलब क्या? अ सोर्स where load resistance is much greater than the internal impedance of the source. That type of source is called as practical voltage source. Let us try to take an example. Let us take an example and try to understand. Ri is equal to say 10 ohms and RL equals to 10 kilo ohms. That means 10 into 10 to the power 3 ohms. तो ये कंडीशन है हमारी, ठीक है, कि Ri is equal to 10 ohms and RL is equal to सिर्फ 10 ओम है और वहां पर लोड रेजिस्टेंस कितना है 10 into 10 to the power 3 ohms. That means 10,000 ohms. So of course RL is much greater than Ri, right? So what is I? I is total voltage, से 4 वोल्ट है ये, है ना, V is equal to 4 वोल्ट है, तो V upon Ri plus RL, right? VI is equal to V upon Ri plus RL. Now can I if I divide the or if I substitute the value, what happens is this value will be V upon 10 plus 10,000, that means 4 upon 10,000, right? This is the value 10010 will be the value, and that will be constituting the current. Some value will be there, and if that current, that means see what happens is it will almost equal to 0.0004, because there will be not much change. And if that value multiplied by the load resistance, what will be the output voltage? The output voltage which I am going to get will be again the same thing, right? See, I'll just explain you. 4 upon 10010, I'll keep the same as it is. So what will be output voltage? Output voltage is current multiplied by load resistance. Current we have calculated 4 upon 10010 multiplied by what is RL? RL is 10,000, that means 10,000, both are almost same, so they will cut each other. What will be the output voltage? Output voltage will be 4 volt. कितना प्रोड्यूस किया था? 4 वोल्ट. कितना मिला आउटपुट में? आउटपुट में V0 पे कितना मिला? ऑलमोस्ट 4 वोल्ट. So we can say that the entire source is delivered at the output. So it is nothing but an ideal voltage source, but it will have internal resistance. Therefore we specify it as practical voltage source. So every voltage source will have internal impedance, but if the load resistance is much greater than the internal resistance of the source, जो भी आप इनपुट में दोगे पूरा का पूरा आपको आउटपुट में मिलेगा. So that is what is the concept of ideal voltage source and practical voltage source. Next is on the same lines we will try to understand ideal current source and practical current source. Ideal current source and practical current source. See, when you define an ideal current source, that means it is a source which provides constant current for any value of load resistance. For any value of load resistance, the resistance which will connect across the output where the output voltage will be taken. So a source which provides constant current for any value of load resistance will be called as ideal current source. So I define an ideal current source. This is a symbolic representation of a current source, say connected to a load resistance across which the output voltage will be taken. So this is the current source. It can be in milliampere, microampere. So this is say IS. Okay, so this is a current source, and of course current will be flowing through the load. If you keep on changing the value of load, still the output voltage will be constant because the current through the resistance will be constant. But if you consider a point, say if the value of RL is say infinite, that means, see, in an electronic circuit, when I say a resistance value is infinite, that means that point is open, no current is flowing through the that particular point. So if no current is flowing through the point, that particular point will be, we say, suppose a switch is there, right? So I will explain you two things. If the switch is open, do you think current will flow through the switch? Of course not. If it is in the open condition, that means in the off state, no current is flowing, and if no current is flowing, we say the resistance is infinite. And as soon as if the switch is connected, what happens is current will easily flow through the circuit. We say RL is short circuited. That means the resistance at that point becomes zero. So this is what you have to understand when I say short circuit, or when I say the resistance is infinite. So when I say resistance is infinite, in case of current source, what happens is it acts as an open circuit. Will there be any flow of current? If there is no flow of current, do this definition still exist? What we said is constant current for any value of load resistance. So if the resistance value becomes infinite, will there be any flow of current? No. So we say ideal current source does not exist. That means there should be some internal path through which the current should flow even in the absence of load resistance. That is what we will consider as practical current source. So practical current source will have a current source, it will have a resistance which is internal resistance of the source, and then we will have the load resistance which is RL. So this is IS, total current, RI and RL, right? Let us take an example and we understand. So when we say practical current source, we say when RI is much greater than RL. See, when I say Ri is much greater than RL, what does that mean? That means in this path the resistance is very high as compared to this path, and current in electronic circuit always takes least resistance path. That means what will happen if the resistance is very high? See, I will just show it by a congestion, okay? And the same box is there, and see, like this. That means if the current has to flow through this, it will have large amount of opposition. If this current has to flow through this, there will be less opposition. That means current will always take least resistance path. So if Ri is much greater than RL, what will happen is the opposition at Ri will be very large. That means all the current will flow through always through RL. So in that case, Is will be equal to the output current which we will be taking. Let's say the current be IL and this current be II, internal current, and the current which is flowing through the internal resistance or the internal impedance, and the IL is the current flowing through the load resistance. Okay, so let us take an example. Now say in this case Ri is 10 kilo ohms and RL is 10 ohms. So there is a significant difference in the value. Now Ri is much greater than RL. So now see what happens is, if I take the output current IL will be equal to the total current Is divided by the total resistance Ri plus RL multiplied by, in a current distribution law, the formula for current distribution law is total voltage divided by total resistance multiplied by the resistance across which the current is not flowing. I'll just explain you what I mean. I is flowing like this, the current will distribute as II and IL, and the current which we are measuring is IL, so the path is through RL. So when you write the formula, it is total current Is divided by total resistance Ri plus RL multiplied by the resistance across which current is not flowing. IL is flowing through RL. So which resistance you have to take? We have to take it as Ri. So what is the value? Of course, say this is 2 ampere. So it will be 2 upon 10,000, right? Plus 10, that value. So it will be 2 upon 10, 10010. So this is the current which will be flowing across the value multiplied by, sorry, here Ri will be 10, it is multiplied by 10,000. Okay, 10,000. So now this 10,000 and this 10,010, right, this value are same, so almost same, so they will cancel each other. So what will be IL will be 2 ampere. So how much is the current which is producing by the source? 2 ampere, and the same amount of current is almost flowing through the load resistance, and this happens when the internal resistance is much greater than the load resistance. So this is what is the concept of ideal current source and practical current source. I hope you have understood. Next we will try to understand different types of theorems. Of course these theorems will be used to solve electronic circuits. So when every time we will try to understand one theorem, let us try to understand what exactly they say and use those things to simplify or to solve the electronic circuit. When I say solve the electronic circuit, basically it means calculating the voltages, current and resistance in the circuit. So that is what is the basic purpose of understanding these theorems. The first one is Kirchhoff's law. So under this heading Kirchhoff's law, we will try to understand two theorems, KCL and KVL. KCL stands for Kirchhoff's current law, KVL stands for Kirchhoff's voltage law. So let us try to understand the statement for KCL. Okay, it's very easy. KCL states that total current entering into the node in electronic circuit. Node is a point in an electronic circuit where you have two or more branches. Okay, so it will be a junction point. Node means junction point where two or more branches are coming out. Okay, so what I said is total current entering into the node. The node is junction point where two or more branches are coming out is equal to total current flowing away from the node. Total current flowing away from the node. So this is the basic statement for Kirchhoff's current law. You have to remember it very well. This can be asked in your board exam. The statement will be given and you will be asked to verify whether it is KCL or KVL or any other theorem. So total current entering into the node is equal to total current flowing away from the node. There is one more statement. The statement is the algebraic sum of total current entering or leaving the node should be zero. The two statement, both the statement mean the same thing. Of course you will understand once we write the equation for a particular given circuit. Okay, the algebraic sum of total current entering or leaving the node should be zero. And whenever you apply Kirchhoff's current law for a particular circuit, you have to use sign convention. sign convention. Current entering the node should be taken as positive and current leaving the node should be taken as negative. Okay, so these are the 2 points. Sign convention: current entering the node should be positive, current leaving the node should be negative. So let us take an example and so this is the point which is called as node. So node in an electronic circuit will have a point where 2 or more branches are coming out. So this is the current, this is the electronic branches. Let this be current I1, let this be current I2, let this be current I3. So from the first statement, what we say is total current entering into the node is equal to total current flowing away from the node. So node is this point, right? The total current entering into the node is I1 plus I2. I1 plus I2 is equal to total current flowing away from the node. The total current flowing away from the node is I3. So from the first statement I can write this equation: I1 plus I2 equals to I3. The other thing is, the other statement is the algebraic sum of the total current entering or leaving the node should be 0. For that you have to apply sign convention. What it says: current entering the node is equal to positive, current leaving the node should be taken as negative. So this, according to the second statement, it will be I1 plus I2 minus I3 equals to 0. Algebraic sum of all the current entering or leaving the node must be equal to 0. Take all the current entering the node is taken as positive, all the current leaving the node is taken as negative. So according to that, the equation will be I1 plus I2 minus I3 equals to 0. So if you take this value as say 1 ampere, say this is 4 ampere, so this will be 5 ampere, right? I1 plus I2, 1 ampere plus 4 ampere will be equal to the total current leaving the node will be 5 ampere. So if you know the current entering the branches, you can easily identify the current leaving the branch. Or if you know I1 and I3, you can easily calculate I2. If you know I2 and I3, you can calculate I1. If you know I1 and I2, you can calculate I3. So this is how Kirchhoff's current law will help you solve a given electronic circuit. The next we will try to understand KVL, that is Kirchhoff's voltage law. Let us try to understand the statement first. It says that the algebraic sum of all the voltage around any closed loop, the algebraic sum of all the voltage around any closed loop must be equal to 0 if we start from 1 point, 1 potential and go back to the same point, same potential. So what it says is the algebraic sum of all the voltage around any closed loop must be equal to 0 if we start from 1.1 potential and go back to the same point, same potential. Of course, we will take one example, we will take one electronic circuit so that we can clear our thoughts regarding what the Kirchhoff's voltage law states. Before going to that, we will try to understand the sign convention. the sign convention follow from one terminal which is positive and come back to the same point and potential to complete one closed loop. So we will try to understand this thing also, what exactly we mean by closed loop. You have to understand that for simplifying the circuit using Kirchhoff's voltage law. So I will draw the circuit diagram. Say this is the circuit diagram, this is V1, this is R1, this is R2, this is R3, this is R4, and this is R5. So of course you have to follow from one positive point and to come back to the same point and same potential to complete one closed loop. See, it is very important that you apply the sign convention properly so that you can understand how exactly we are moving. See, this is the positive terminal, this is the negative terminal. How the current will flow? Current will always flow from positive to negative. So to observe this circuit, let us name the points. This is A, B, C, D, this is E, and say this is F. So now what you can see is, first you apply the sign convention depending upon how the current will flow. So how the current will flow? Current will flow from positive, so it will move like this, it will move from R1. When it is moving through R1, it will develop a potential difference, right? Potential difference, I'll name this as V. So potential difference will be like this, positive, negative, and the potential be say V1, okay? Direction of current. Now the current will go like this, it will come here, it will move towards R3, it will move towards R2. When it will move towards R2, the potential will be like this, plus minus R3 plus minus. Then the current will move through R4, so plus minus. All this current will enter into node E and then it will go through R5, so plus minus. So these are the sign convention which has to be used on the basis of the current, the way in which the current will be flowing in the circuit. Okay, so now let us try to identify the loop. So in this circuit, of course, you can see I just want you to interpret how many loops we have. Closed loop, starting from 1.1 potential going back to the same point, same potential. So the first loop, loop 1, is A, B, E, F back to A. As I said, we will start with one positive potential and we will go back to the same positive potential. So loop is A, B, E, F back to A. So when you are moving from A to B, what is the potential here? The voltage is V1. As we are moving from positive to negative, we will keep that voltage as positive. Next, B to E. B to E, when you are moving, it is moving through R2. Let the voltage drop here is V2. Let this here is V5. This is V3 and this is V4. So when you are moving from B to E, it is V2, and we are moving from positive to negative, so it will be plus V2. Then E to F, we are moving from positive to negative, plus V5. And then when you go back to the same terminal, we are moving through this potential V, which is moving from minus to plus. In all these conditions, we are moving from plus to minus. Here we are going from minus to plus. This potential will be taken as negative, so it will be minus V equals to 0. So the algebraic sum of all the voltage around any closed loop. I hope you have understood what exactly I mean by the closed loop now, है ना? So this is the first example, A, B, E, F back to A. So that is a closed loop starting from one point, one potential, going back to the same point, same potential. So the algebraic sum must be equal to 0. So that is what we have done. Okay, so this is the equation, or I can say V1 plus V2 plus V5 equals to V. Next, loop 2, second loop. Take the bigger one, A, B, C, D, E, F back to A. A, B, C, D, E, F back to A. So when you are moving from A to B, it is V1 moving from plus to minus, B to C moving from plus to minus, plus V3, C to D moving from plus to minus, plus V4, D to DE, of course there is no resistance, so no voltage drop, and E to F, we are moving from positive to negative, it will be plus V5. And then when you go back to A, it is moving from minus to plus, so it will be minus V equals to 0. So V1 plus V3 plus V4 plus V5 equals to V. Okay, so that is according to the loop, second loop. And there is one more loop in this circuit. The loop is, we can start from the positive terminal of node B and we can go back to the same positive terminal. So when you move from B, so it will be loop 3, B, C, D, E back to B. So when you are moving from B to C, it is V3, right? B to C, positive to negative, C to D, positive to negative, we are going as V4, D to E, there is no resistance, and when you are going from E to B, we are going from minus to plus, so it will be minus V2 equals to 0. So V3 plus V4 equals to V2. So in all these three equations, the first equation signifies Kirchhoff's voltage law. The algebraic sum of all the voltage around any closed loop must be equal to 0, starting from 1.1 potential and going back to the same point, same potential. So if such an equation will be, if such equations are generated, and if you know the value of voltages around any particular closed loop, you can easily calculate the voltage drop around the other closed loop. So that is the advantage of Kirchhoff's voltage law. That is the objective of understanding Kirchhoff's voltage law. So now what we will do is, we will implement KCL and KVL in the circuit to calculate current and voltage. So this is the most versatile theorem because it doesn't depend upon series and parallel combination. This law is true for all electronic circuits. So let us take one circuit and solve using Kirchhoff's current law and voltage law.